I am Jake Althouse with Frost Engineering and Consulting. I'm here to talk about Pultruded FRP structures.
Welcome to the Structural Engineering Podcast. This week, we're talking with Jake Althouse, a Pultruded FRP enthusiast if there ever was one. Talking to Jake, you get the feeling he's somehow capable of not only designing FRP, but even manufacturing and assembling it if he needed to. FRP is a very cool material that I've just barely got the chance to design with. I think in its niche, it's a phenomenal option that's hard to beat. So with that, let's find out what there is to know. First, can you tell us what FRP is? In my head, this is also fiberglass. What's the short word? When you're talking to someone in the field, are you saying, hey, could you grab a piece of Pultruded FRP? Or, what's the slang here?
I generally would just say FRP. Okay. But I did recently re-listen to your episode with Aniket about, bonded FRP on reinforcing concrete structures. This is a bit different in that we're not applying the FRP to another, structural material. This is its own structural material. Similar composition, though. There's either glass fiber or carbon fiber, which is surrounded by a resin. That resin can be in a couple different types of epoxies. But generally speaking, it's glass fibers encapsulated with a resin. I guess I'll go a bit further to answer your question on Pultruded. I throw that around lightly, but a lot of people don't really know what that process is. Basically, it's the process by which the FRP is made. There's several ways to make, composite materials. And pultrusion involves basically pulling the glass strands through a die while simultaneously injecting the resin, which is thermocured, which means as you heat it up, it will set. So they basically pull all of these huge glass fibers all down through a specific die, inject the resin at the perfect time, heat up the die, and then out comes, the FRP shape.
How long can these things get? Since we're kind of on that topic, can you get these in typical steel lengths? If you can truck it, you can get it in?
Yes. I actually asked that very same question. I recently went and visited one of our the predominant producers out in Bristol, Virginia, and their answer was if we can physically have the space for it to come out of the machine, we can keep pulling.
Cool.
Funny enough, I actually heard a story that they have actually cut holes in the block wall to allow the material
to push a piece out.
Which was crazy to me, but they can, as long as you can accommodate the standard tolerances, similar to steel, right? There's mill tolerances for straightness and out of plumbness and things of that nature. As long as you can accommodate those standard tolerances, you can get it really as long as you can fit on a vehicle.
Wow, that's pretty neat. When Max brought up this episode to me, I have to say, very ignorant to the topic. Have since learned a little bit more about FRP. But one thing that came up, initially was when and why would you use FRP?
So we have seen over the course of our years working with FRP, there's kind of two main boxes that the FRP projects can fall into. First and foremost, and probably the most predominant, is a corrosive environment. And corrosive in this instance can be pretty widely varied. We've had salt plants, which will eat and corrode, galvanized or stainless steel in a relatively short amount of time. Acid producing plants for batteries and other type of, industrial uses for acids. The water and wastewater industry, which you can get some pretty corrosive substances in those environments. That's kind of the first bucket, let's say. The second is, given its light weight and I guess relative ease of production, and I think most importantly, lack of a need for secondary corrosion protection, is quick deployment, rapid deployment projects. we've had several projects where we're able to value engineer a secondary type appurtenance and deliver and erect the structure before the steel arrival date.
Jeez.
So, particularly in the mission critical field, if you guys are familiar with that term, data centers and other types of structures of that nature, particularly out in the yard, which is why I said secondary structures, something that's going to support water conveyance or, maybe electrical appurtenances or mechanical appurtenances uses or means to access and maintain that type of equipment. We just thrive. You don't need to maintain the structure nearly as often as a steel or other type of material. You can deploy it very quickly, given its lightweight. It makes a lot of sense, I guess, in that environment.
Given the things that it can help protect against, you said acid and salt and stuff, is there anything that uniquely attacks FRP? Just for just for the other side of the coin, there is like, oh, you can't, whatever. Is UV? I mean, anything?
Oh, that's an excellent question, actually. And I will say that even within those environments, there are particular types of substances which will corrode FRP, or at least will diminish its useful life. Every FRP producer generally has like a set list of things it works well with and things it does not. But even within that, I did at the beginning of the episode point out that there are many kinds of resins that can be used in this process. The two most common, I would say, are polyester and vinyl ester resins. And between those two, you can really probably accommodate, I'd say, 90% of materials or substances you run into. And if you have a really unique situation, as long as the volume of application makes sense for the producer, they'll generally be more than happy to make you a custom resin mix to meet that specific environmental requirement. And you asked what sort of things makes FRP not a good fit. And actually to that, I would say the same answer as Aniket gave was fire or elevated temperatures in general, let's say. If you have a high sustained heat, you either need a specialty resin specific for that application, or it's more than likely another material is going to make more sense.
Yeah. In the example projects that we were talking about, a couple months ago, there was one I recall that had a high sustained heat. It was, I think, access to a cooling tower. What is sustained in this case? Is that 150?
Generally speaking, if you're below 90 degrees, you don't need to reduce your strength or your stiffness. If you're in the 100 degrees to 150, FRP can be used, but you need to accommodate the reduction in both strength and stiffness.
Okay.
Above 150, like I said earlier, you're probably going to need a specialty resin in order to meet that.
Cool. Yeah, I just wanted a number to it in my head. This is probably a number I don't remember correctly, but high temperature for wood is over 150, I think, right? So
I believe so.
I have, tried to design with FRP one time. I didn't get that far, and we went a different route. So that might come up a few times in this discussion. My education stopped abruptly and went elsewhere. One thing I was digging for when I was trying to do this design was design guides, or sort of a code book, an industry standard that we have with steel and concrete. Are there those resources available?
The answer is yes and no.
Okay.
So recently, ASCE, in conjunction with ACMA, which is the American Composites Manufacturers Association, hosted a public comment period for a new standard, which is ASCE 74, load and resistance factor designed for pultruded fiber reinforced polymer structures. Quite a mouthful, I know.
Yeah.
But the provisions of this standard are based on a pre-standard which was published in 2010. So that is what I would say the current standard of practice if you're trying to follow, the a design standard similar to the other building materials. Beyond that, each pultrusion manufacturer generally has their own design guide, similar to like a unistrut or even wood, right? I will say that those design manuals generally have, basic column strengths, beam strengths, recommended connection geometries, but they don't necessarily give you enough information to design a full structure. The most readily available one that comes to mind is seismic provisions. The only place you're going to find seismic provisions for FRP is in that ASCE 74 document. So yes, the information is there, but generally here at Frost, we found that to effectively design with FRP in a building type structure environment is we've amalgamated all these resources from different parts of the industry. Mm-hmm. Europe has a code, the Euro code, which we've referenced from time to time, and just all of the different testing documents that the pre-standard references. But we physically have found those documents, reviewed them ourselves, even found connecting documents to that. So we've spent several years just kind of getting this bank of knowledge, if you want to call it that.
Absolutely. With all this stuff that you've gathered, what has the response from plane reviewers been? Are they, asking for a specific code? I feel like they are the type to be a little more strict on, this is not American code, this is not codified, or whatever the case.
So generally, our design follows that ASCE document, which was just referenced as a pre-standard, which is now conjectured to be ASCE 74. That is our standard of design. And the only time, or I guess I won't say the only time, but generally if we go outside of that document, it's because that document doesn't contain the information we need. One topic very close to my heart, which I won't get into much detail here, is but a prying action, which I'm sure you guys have heard of it for steel. They address prying action in FRP as it needs to be, you need to accommodate. Yeah, you have to consider it.
I love those lines.
Yeah, which I don't, obviously we're in our infancy with this type of material. I understand, why that's the current provision, but when that sort of thing happens, we have to seek, the best information we can elsewhere, and using our engineering, judgment, apply it to our application.
Okay, so let's say we've got a steel building we've designed, or something similar to a building, and we want to substitute FRP in for that for a magnitude of reasons. Do they make the same shapes? Are you doing the same pieces? A wide flange is the same wide flange, and how does that work?
So I'll answer your question in two parts. The first part is I'll address your specific question on shapes. The generic shape profile, if they make it in steel, they make it in FRP. Now, the ratios of thicknesses and depths and all of that, we don't have nearly the array that steel does. Generally speaking, as far as eye shapes go, you fall into two categories. It's symmetric in depth and width, and the flange and web are the same thickness, or the shape is twice as deep as it is wide. That's the most commonly available shape. So a 12 by 6 is probably, I would say, the most common. And for columns, a 6 by 6 by 3/8 or 8 by 8 by half. Those would be the most prevalent. Obviously, angles, channels, and then more secondary type shapes, I would say, like handrail, kick plate, decking. There's a huge array, I would say, of shapes available. I will also say, similar to aluminum, we have the ability to make some really unique shapes. If you need a shape to fit a very specific, need, as I said earlier, as long as economically it makes sense, a lot of producers are more than happy to work with you to make this new shape. For instance, we are working with a company to develop a rail, kind of like a unistrut type device, which would be used on top of RVs or motorhomes to support solar panels. And going to an FRP type material, eliminates the potential for corrosion over time, and it also reduces the weight, which would improve fuel economy.
That's super cool.
I thought was just fascinating.
As someone with a solar panel on top of a camper, that's sweet.
Yeah, and we've had several projects similar to that where somebody's come to us with a need and they felt FRP might be a good solution, and we got to kind of work through the beginning stages of product development, just structurally fitting the best shape to the particular need. So I'll call that part one of my answer. Now part two, you said if you had designed a steel structure and wanted to replace with FRP. Now, given the inherent composite material properties, a straight up swap from steel to FRP is just not possible at this time. There's locations in a building that FRP makes a lot of sense, and there's other locations where it just does not make sense. For instance, probably the primary hindrance, I would say, of FRP right now is its lack of stiffness. 1/10 of the stiffness of steel. So a modulus of elasticity of about 2,500 to 3,750 is what I would say the common number is. In comparison to, everybody knows the modulus of steel, 29,000. So if you have a particular element that's going to be governed by stiffness, say a really long span beam, or the column in a portal frame, or something of that nature, FRP isn't going to be your best solution. Now, where we find a lot of great applications in buildings is infill framing. I talked a bit about our mission critical projects. Data centers, the interior data center space is more or less the main building structure, keeps the weather and elements off of everything. And then there's a secondary structure inside of that supports all of the mechanical, electrical, plumbing appurtenances, electrical and pipes and all sorts of arrays of things. That interior structure is a perfect fit for FRP. It, as I believe we kind of talked about earlier in the podcast, it's lightweight. We developed a custom shape that would span 20 to 30 feet, and it's about 18 inches deep, 8 inches wide, and weighs about 17 pounds a foot. Now, if you look in the steel manual for any 18-inch shape, you're not going to find anything in the 17 pounds a foot region. So just being able to bring these materials into an existing structure and erect, the new interior structure, you just can't beat the maneuverability, I guess.
Yeah.
So to kind of keep building on this, I want to make sure that I've kind of set the stage of the material, and you kind of started bringing up the properties of it. And I know we're going to want to get into some heavier topics, but just to keep it the basic level, what is, I think everyone is really familiar with the stress strain curve, let's say, for steel, and that drives into ductility and maybe something we'll get into. What does that look like for FRP?
I'm going to start by saying I'm really appreciative that you guys want to get into this. This is one of my favorite things to talk about, honestly. But as you said, everybody's relatively familiar with the stress strain curve of steel. So you have the initial linear elastic portion. Then you have the plateau into plastic behavior and strain hardening and the ultimate rupture. FRP doesn't have a yield. Being that it's a resin material with glass fibers, those glass fibers are a brittle substance. Once you reach the material rupture, it ruptures. There is no plateau. There's no strain hardening. It's more or less linear elastic to rupture. So just that initial point or portion of the stress strain curve for steel is where we kind of live.
Are you using because it's a little less ductile or prone to yielding? Do we generally have a lower fee factor in these products then?
Yes.
Yeah.
and I know, not everybody listening can see my reaction, but given the infancy and kind of how young the code is, and the lack of data to pull from, we have some fee factors that are generally much lower than other building materials. So everybody is generally aware of fee factors for more ductile limit states are generally higher for those more brittle limit states. Now, given we don't have a lot of ductility, really the best one I would say is global buckling. That's a great energy dissipation mode. Given we don't really have a lot, fee factors of 0.5 to 0.6 are pretty common. And a lot of I guess I'll build on that just a bit. There's a lot of limit states akin to these composite materials that not everybody would be familiar with. If you've done a lot of wood, then some of them will look more familiar than, say, someone who's done primarily steel.
Mm-hmm. I think we kind of went over the material, but what about like attaching to it? You brought up wood and stuff, and I'm like, okay, wood, you're throwing a nail into it. Maybe you're shooting in something, powder actuated fastener. Obviously, you're not. And maybe this is a great question. Is there resin welding that is also occurring in any of these any of these projects? Can you talk a little bit about what the attachments look like?
Sure, and I'll generalize that if you're okay with this to connections. What does a connection look like? Primarily, I would say the large majority of connections between FRP elements is bolted using some sort of clip angle, like you would see in steel. Now the hole oversize is a 16th, similar to steel. Pitch spacing and gauge spacing is a little larger than steel elements. Particularly edge distances are a little larger, but proportionally speaking, they look a lot like bolted steel connections. So welding is something I really miss as someone who does a lot of FRP work. Steel, you can solve a lot of unique problems by welding. Sadly, we don't have any welding per se, but adhesive connections are gaining more and more traction. And when I say adhesive connections, I mean an adhesive specifically made for this material. There is some data available for the general construction adhesive, but primarily if we're using this adhesive for a structural intent, it's a very specialty urethane type adhesive that bonds this type of material. So outside of bolts and adhesives, we've had some select projects where we've used self-drilling screws in a roof structure to attach the deck down to the substructure below. And there is some marginal amount of data out there for justifying that type of connection. Nails, we've not got into yet, but I will say, given I'm around the material a lot, I have some that I've taken home with me to kind of play with because I'm a hands-on kind of guy. I also am I would call myself a handyman, so I happen to have a powder actuated fastener. Right? So I was curious. Like wood, concrete, use these all the time. Cold form steel, another big industry where we use cold or powder actuated. So I was curious. Yeah, how would it go? I'll actually say. I could see an excellent application similar to cold form steel, maybe anchoring to an existing concrete element. I think it could absolutely be a great application, but the data available to me is as what I've done personally. Anecdotal. I've also seen a bit of data on using a powder actuated fastener to attach FRP strips to masonry. So I know some amount of research has been done to that. I truly think that would be an excellent, realm for future, research, is these fasteners outside of bolts, I guess.
Awesome. We keep saying bolts, and I've got a dumb question. What are these bolts made out of? Is this like just steel bolts, or are there FRP bolts if you need that in the application, or some composite style material?
So actually, both exist.
Oh, cool.
Obviously, steel bolts anywhere and everywhere. We generally either use A325 because of its availability, or if it's a corrosive environment, sometimes we'll use stainless bolts, either A307 or A316. I would say that's the vast majority. We use a steel type bolts. Now, we have had some really unique projects where, and this was an application I didn't mention earlier, FRP or composites in general, most of them are inert to radio interference. So if you have, say, a structure where you need to really limit the amount of radio interference, like the top of a tower that has an antenna, FRP is perfect. It can. I know I'm no expert in that particular field, but it's invisible, I guess, to the radio waves. And to further reduce the impact we were having on the equipment, they actually asked if we could provide a fiberglass bolt or an FRP type bolt. And we did find a company that makes them. It's more or less a continuous round rod in which they would cut the threads after the fact. And where that kind of posed a unique challenge, and I believe we lightly touched on this earlier, but I think this is a good opportunity to revisit UV degradation you asked about. Fiber blooming, a lot of people are familiar with that term. Basically, if you include like a fibrous material in concrete, over time the surface can look kind of fuzzy, or even like composite, like lawn chairs are a great example. If it has a fiber reinforcement, it'll kind of look fuzzy over time. And why that happens is the sun's UV rays degrade the glass. The glass starts to have local failures. You start to see the ends of the strands, and that's why it starts to look kind of hairy. Obviously, we don't want to corrode our primary tension reinforcement. So most pultruded products today come with what's called a surfacing veil. So we have this bundle of glass fibers in a resin matrix, and then around that whole profile, they wrap a specialty fiberglass mat that basically is a sacrificial layer, if you want to call it that, to protect all the glass within. It's also impregnated with some admixtures that help resist UV degradation. And why that kind of plays a part into the fiber bolts that we were talking about is when you cut the threads after the fact, you obviously damage that veil, that surfacing veil. And so the glass fibers are exposed to UV, and you have the potential for accelerated corrosion or degradation. So generally speaking, you want to use these bolts in an interior environment, somewhere where you're not having that constant sun exposure.
I just keep bringing us back to some basics. My mind works like I need to have this really great foundation right before we start really going up. And so I apologize for some of these questions, but with most structural materials, and especially with concrete, we think about how's it going to fail, right? You want to be able to observe concrete about to fail before it fails. You don't want it just to fail instantly. So by observation, can you see what does the material start doing prior to it failing? Let's say in bending or in shear. Is there an observable piece to that?
Absolutely, and I'm really glad you bring this up on, identifying modes of failure. And I think, that's a really great piece that, good structural engineers are going to focus on. Not will it fail, how. So to now answer the question relative to FRP is the most common limit state for let's focus on connections, because that's, the critical, in my opinion, piece, is splitting. So it's not necessarily a section rupture, like say block shear, but it's a local, the lamina of glass held together by the resin separate. So you would crack or split the material. Now, this limit state doesn't mean that the structure has lost all ability to resist load. It just means that you're going to have, an accelerated rate of deformation at the joint, but not a immediate loss of strength. So that failure mode does give a bit of warning. Obviously, the auditory, you'll certainly hear it, and being in the lab pretty often for some of our testing, it is almost like a gunshot. Hearing these materials separate. So you'll have that auditory, but beyond that, obviously the visual. Hey, there's a large crack that's starting to propagate from this region. Let's vacate the premises and come back and do some sort of inspection. So connection wise, that's our biggest, what I point to a lot as far as a warning sign. Going to material side, for primary flexural members, the general limit state is like a local compression buckling, a compression flange. Which isn't, a really great limit state for giving a lot of warning. Mm-hmm. A lot of times we have a deck up on top of the structure that would be, periodically connected, like an open bar grating for a dunnage type structure. We generally, ignore any benefit of that being there, given we don't, specify a repetitious connection pattern and the stiffness in one direction. I mean, you guys have seen bar grading. It's not exactly, a really solid material. We generally ignore it when doing our calculations, but at least keep it in our pocket that, it will do something. There is a difference between element performance and system performance. Mm. So the chances of a local flange buckling phenomena is, I guess, reduced a bit by the presence of whatever's on top. Columns are generally flexurally driven, and that's because, and we'll, I'm sure, get back into this, but with not being able to weld, moment frames aren't nearly as prevalent. So we have a lot of braced frames. And pulling the work point of your braces down into the column is generally preferred, so we avoid any sort of gravity loading on our lateral force elements. But in doing so, we've now induced an eccentricity in our column, which causes some flexural demands. And given the reduced stiffness, we generally don't have a really high flexural strength in our column sections. So that's actually, in my opinion, a benefit, giving it a flexural mode of failure rather than a compressive type mode. So that's kind of the gambit of what I see as the controlling modes in a lot of the different elements.
Okay. I assume this material is a little bit like wood in that the analysis has to take into account the direction of the grain, so to speak. Is that accurate, that if you are pulling tension perpendicular to the grain, that may be the weaker mode, and if you are bending with the grain, that is probably the stronger?
Yes, that is true. I will say I'm a bit jealous of wood designers in that, there's that wonderful equation up towards the front on bearing at an angle, or being able to capture a strength at any direction, I guess. Given the two principal, strengths, you can find anything in between. We currently don't have that provision in FRP. And I will say that let's call it strength, as you look from, let's say, perpendicular to, along or parallel, it doesn't necessarily linearly relate as you change between 0 degrees to 90 degrees. There's actually the weakest, if you want to call it that, direction is somewhere, I believe, around 30 degrees for most common shapes. So given that our stress profile isn't exactly a straight line interpretation, and every shape having a different, orientation and percent inclusion of glass fibers, they're all going to vary, which is why I think we don't have that current provision. Now, I guess to come all the way back, we have 0 to 5 degrees relative to the grain or pultrusion direction. That is the strong direction. If you're beyond 5 degrees relative to the pultrusion direction, you have to use the minimum weak axis properties. So
that hits you pretty quick.
If, say a column, if the column is primarily a gravity member, but you have 6% of the gravity load as a shear, we're already in the weak properties.
Wow.
So that in conjunction with the reduced phi factors, the reduced stiffness, you can start to see why designing with FRP in some instances becomes quite cumbersome.
Yeah, really.
So you design FRP. And I'm sitting here thinking, okay, we talked about design guides kind of out there, talking about materials, or, there's some sort of specification of shapes and sizes out. Am I, as let's say the engineer of record, actually designing it and specifying it, or am I saying this is an 18-inch FRP shape designed by others?
So we've actually had projects kind of go both, where the entire design is delegated, and it will be something to the effect of, access platform by others. And we've also had projects where an EOR will attempt to accommodate a preliminary FRP design, and we're asked to more or less validate or provide a correction or an alternate suggestion. I guess we'll put it that way. Primarily, I would say it's the former. They'll just delegate the entire secondary type structure, and we'll be responsible as the delegated designer, and even provide signed and sealed design packages for that. But as I said, we have had a couple projects where we'll more or less design the structure, review it with the EOR, and they'll include that in their package under their seal. I personally prefer us taking full responsibility for it. It makes me feel more comfortable, especially given not a lot of people have a lot of comfort with FRP, and that's just, it's new, right? I'm not faulting anyone for that, but in that instance, it makes a lot more sense to defer to the engineering judgment of someone who uses it more than you do, I guess. So I prefer that route just for project success.
Yeah. I want to talk about moment frames and brace frames. I think now I know we've got a lot to talk about moment frames because you're helping on some research for this, I think. But let's do brace frames first, real quick, since I assume that is the most common method for bracing a FRP structure. Are there any sort of nuances that we should know about besides our typical brace when we're looking at a brace frame?
So I would say that a nuance with steel would be we don't have what I would call an eccentric brace frame, or we don't use them nearly as prevalently.
Yeah.
Or knee braced frames, something where the work point is in the beam. And the reason for that is if I am imposing a constant stress, similar to wood or concrete, FRP is prone to creep. So if you have a long load duration, we actually have to accommodate that by reducing our strength based on an anticipated duration. So when we start, imparting an eccentricity or a work point in a flexural member, or let's call it a gravity member in general, those permanent flexural stresses really diminish how effective FRP can be. So knee brace frame in, say, a live load event is going to induce both a positive flexure in your beam and a strong or weak axis flexure in your column. So we generally try to avoid that. Mm. And I touched on that a bit earlier, where that's generally why we would pull the work point of the brace down into the column, or concentric with the beam column work point, such that we're not anticipating a gravity load in our lateral force system.
I see. Okay. So, yeah. And now I guess looking at the moment frame, is that possible? What is that connection like? How do you make a moment frame out of FRP?
So this is a really cool realm we've recently kind of dove into, and it came out of necessity. We were looking at a low-rise access platform, which I believe is in Arizona, and it was so low-rise or short in height with so much MEP equipment below that braced frames just weren't possible. There wasn't enough clear space to deploy a braced frame. So in that instance, we said, well, we've got to make a moment frame. How are we going to do this? So where we landed was an adhesive. I touched on this earlier. Rather than welding, we use adhesive to provide that rigid joint restraint. And given this was a specific project application, the ASCE pre-standard and ASCE 74, which is the potential standard coming out, I believe, next year, gives an avenue for validation testing. Basically, if you test so many samples, you can develop a phi factor and a nominal strength, and then validate the product in that way. So we went that route. Just given there was no other data really available, or very limited data, I'll say. So we partnered with the University of Notre Dame, which is also here in northern Indiana. I think we're 20 minutes from campus. So yeah, it made a lot of sense for us to skip on over and work with them. But we were able to develop a wide flange column to wide flange beam connection, in which the webs of those elements are adhesively bonded together. So you can imagine in your head, you'd have to locally strip the flange on the bottom side of the beam and the leading face of the column to allow that lap to happen. And then within that lapped area, we still have bolts, which would be from the incoming beams coming into the column. And I know that's a lot to mentally picture. More or less, we have web-to-web bonded with some bolts that would eventually be used in a clip angle for a beam connection.
But no flange connection?
No flange connection, which, it's wonderful you brought that up, given steel, if you don't connect the flanges, well, it's not a moment connection. But given the small surface area of the flanges relative to, obviously, the web-to-web could be 100 plus square inches of adhesive area, a very large area. Whereas, a half-inch thick flange, 6 to 8 inches wide, that's just even. And let's go into manufacturing tolerance. If that's not perfectly square, you're not going to get a good bond to the other element. So we targeted just bonding the webs, understanding that wouldn't provide at peak optimal stiffness given the flanges weren't engaged, but we didn't feel the tolerance was there to really deploy that kind of connection. But I guess to continue on the subject, because I really thought it was interesting, and I think you guys will really like to hear this, given we talked about the stress strain curve of steel already, is we actually found that type of connection had two separate, very distinct plateaus. And the initial plateau was more or less linear elastic, and that was the adhesive, acting similar to, say, a weld. there was very little slip, if any. And so you had this really high initial rotational stiffness up into where the adhesive sheared due to that applied moment. Once that adhesive sheared, the bolts obviously are still in that plane, so there was a lot of initial rotation in order to take up all the slop from the bolts. But once the bolt pattern was fully loaded, we actually reached what I would call an ultimate strength that even exceeded the adhesive strength. And we pushed the test all the way to physical failure. We actually ripped the flange off of the web. It was really cool to watch. But yeah, so you had similar to steel, you have the plastic range where you have large amounts of deformation for very small increase in stress. Which is more or less what we saw. Is we had this really large, amplification of lateral deformations, but we didn't lose the ability to resist demand. Yet we had this second kind of plateau of strength that even exceeded the initial. And I really felt comforted by that, in that, we have this initial stiffness, let's say for like service level events. If like California, if we're working out there, we don't want, the fairly common seismic event to debond all of our moment connections, because at that point, it gets pretty wobbly. You have a lot of lateral deformations, I guess, which wouldn't really fit the application. So if we can design, a service level event to fall within this debonding zone, so that, we still provide the day-to-day performance. And then we have this ultimate state where, we go beyond the adhesive into the actual, bolted connection at, an ultimate event. I think that would be, adequate performance. If it doesn't collapse, if, everybody that was using it exits the structure and is, safe, yeah, that's a win for me.
Yeah, oh yeah.
Obviously, there'll be a lot of repairs that need done, but at that point, the structure has served its purpose. So I think it's really neat that we have the opportunity to look at these two different service levels, which you guys have touched on, the performance, or what's the term here, where you have a specific criteria that you're trying to meet at different service levels. But it's really nice to me that we're able to look at those two events kind of separately.
And I guess I should ask the quick seismic question is, if you're doing project in California, what R are you anticipating? Is there is kind of an R of one style structure just for now, or is there some ductility assumed that you can reduce your forces a little bit?
So we more or less have two options. There is R of 1, which is the primary, that's what's used most often. Yeah. There's also an enhanced strength kind of criteria. There's some requirements for connection strength and over strength and redundancy that you need to meet. But if you meet all of these requirements, you can actually use an R of 1.5.
Okay.
Now, similar to all other buildings, if you have mixed systems in two different directions, you need to use the lowest R. So a lot of times we end up at R equals 1, even if we have some frames that meet this enhanced connection strength criteria, just because one of the criterion for enhanced strength is that it's multi-tiered. I believe the thought is you have a bit of redundancy there. If you have a multi-tier X-brace frame, even if one brace does fail, you still have its pair that could act as a tension-only brace. So I think they're just counting on a bit of redundancy there.
I see.
But so if we have a single-tier X-braced frame, we automatically don't qualify for that enhanced.
Oh gosh. Okay. Yeah.
So we're at R equals 1.
Yeah. Okay. I think the last questions we have, I should throw out as almost quick ones. Software packages. Is there anything specific to FRP? How are you guys doing your analysis? Is it just kind of pull out the results from a frame software package and then do what needs to happen to convert this to FRP?
So you asked two questions with varying answers.
I tend to ask two questions at once. Yeah, it's a bad habit.
So, to my knowledge, no, there's no package that will design FRP for you. We've developed a lot of in-house, spreadsheets to help with this process, and we use a finite element software. Visual analysis is what we use primarily, to determine all of the member reactions and even perform, dynamic modal analyses. Export the results into our in-house suite of spreadsheets.
Okay, that makes sense. And manufacturing material availability, do most states have a plant or a facility that stores this stuff, or within an adjacent state? Is it easy to get everywhere?
I haven't heard of a lot of material availability issues as far as the projects we've worked on. We primarily work with, I would say, 3 manufacturers, and I know they've supplied product, as far as Alaska all the way to, the Bahamas.
Well,
so I don't believe material availability is a big issue.
That's all for now. If you've enjoyed this episode and would like to hear more, let us know. Jake is tremendously informed about the FRP industry, and luckily for us, he's happy to share that knowledge. We may do another episode with Jake to dive a little deeper into some of these topics, so please reach out with any questions you have for him, or any pieces of the FRP puzzle you'd like to know more about. Thanks for listening to the Structural Engineering Podcast. See you next time.